Okay, so in this lesson of integration using substitution method, we're going to look at a fourth strategy, and I call this a two-step substitution. And I call it that because after we define our u variable and our du, and we substitute everything in, we're going to be left over with some excess x variables that we're going to have to convert to u using the definitions that we set up. So if we look at our first example, we can say, let's make our choice for u. From previous lessons, a good starting point is to look at an internal function. And we see that 9x squared minus 1 is inside of the square root function. So we're going to say let u equal 9x squared minus 1. If that's our u variable, then the derivative du is 18x dx. And when we look at our problem, we say, well, I have the 18, I have the x, and I have the dx, but we have too many x's. We only needed 18x, we have 18x cubed. So I'm going to break this up so that I can see the substitution a little bit more clearly. And then we're going to modify our substitution using u equals 9x squared minus 1. So you can see what I've done here is I've taken the 18x out of the 18x cubed and I placed it next to the dx. And in doing so, I have now everything that is equal to du grouped together, and that part of the substitution is clear. I have my internal function set as u, that part of the substitution is clear. This is what I need to fix. So I go back to my substitution. I say, well, since u is equal to 9x squared minus 1, I can solve u equals 9x squared minus 1 for the x squared variable. So I'm going to add 1 to both sides. So then u plus 1 is equal to 9x squared. Add 1 to both sides, and that's what we get. And then if we divide both sides by 9, we get that u plus 1 divided by 9 is equal to x squared. So now I know what to do with my x squared in front of my integral. I'm going to replace that with u plus 1 over 9. So all of that said, I now have a second rewrite of my integral. I'm going to change the square root of 9x squared minus 1 to u to the 1/2 power. That's what we always do with integration. We change square roots to the 1/2 power so we can use the power rule for integration. And the 18x dx becomes my du. And just to simplify this a little bit, I'm going to take that denominator 9 and put it out in front of the integral as 1/9. We can do that with constants. And now we use distributive property to change these terms to be strictly terms of u. And these are terms of u that I can now apply the power rule to. So we're ready to take the antiderivative. When we add 1 to the exponent of u to the 3/2 power, we get u to the 5/2 power. And when we divide by that 5/2 power, we get 2/5 u to the 5/2. When we add 1 to the exponent of u to the 1/2 power, we get u to the 3/2 power. When we divide by 3/2, we get 2/3 u to the 3/2. And we have our antiderivative now. The next step is let's return that u variable back to a variable of x. So we're going to replace u, every instance of u, with 9x squared minus 1. So we'll continue this on another page. So we have 1/9, and then 2/5, parentheses, 9x squared minus 1, to the 5/2 power. We do the same thing with the other u variable. And finally, we can distribute this constant that we put out in front of our integral. This is our final answer. And as always, if we want to check our final answer, we can take the derivative. Remember, we would have to use derivative with chain rule. And then we would compare it with our original question to see, does it match up with the function inside the integral. Here's our next example. Again, we would use our skills that we learned in previous lessons, and here we would say a good place to start is to choose the denominator as u. So if we let the denominator be u, that means u is 3x squared plus 7. The derivative gives us du is equal to 6x dx. And we say, once again, the numerator has a 12x cubed. I just need a 6x. I can break apart the numerator. And once we have this, we can see that everything over here is our du. And we see that the denominator is our u. And once again, we have extra. We need to replace that x squared. The 2 will just move out in front of the integral. It's a constant. But the x squared we need to replace. So we go back up to our definition for u, and we say, let's solve for x squared. So that's going to give me u minus 7 over 3 is equal to x squared. And now we can rewrite our integral, putting the 2 out in front of the integral. I'm replacing the x squared with u minus 7 over 3. The denominator is u. I'll put that in the denominator. You can use keep, change, flip to verify that you get 3u in the denominator. And the 6x dx gets replaced with du. So now that we have this, we can say, well, I have another constant I can move out in front of the integral. So that gives me 2 over 3 times the antiderivative of u minus 7 over u du. And we can simplify this with monomial division. U divided by u is 1. 7 divided by u will be minus 7u to the negative 1. And then we have our du. And once again, we can apply the power rule. So we get 2 over 3. The antiderivative of 1 would be u minus 7. This is one of our memorized antiderivatives. U to the minus 1 gives us the natural log function of the absolute value of u. And then plus c. And now we want to return u to its x variable form. So our final answer Now maybe you notice that I changed my natural log from absolute value to just parentheses. We can do that if the function inside of the natural log will always be positive. Well, x squared is always positive. Anything squared is going to be a positive. Multiplied by positive 3 will be positive. Add 7 will be positive. So that argument will always be positive. We are able to change the absolute value brackets to parentheses since the expression inside the log was always positive. If there's a chance it could be negative, you would leave it as absolute value. So let's look at this next example. Once again, this is my internal function. It's inside of the cubing function. So I'm going to say let u equal 4x squared minus 8. Then du is going to equal 8x dx. And I'm going to solve for x squared is equal to u plus 8 over 4. Because I already anticipate having extra x squared in there. I also have an extra 2. So I need the 8 and the x and the dx for my du. The 2 is going to go in front of my integral. The x squared is going to be replaced by u plus 8 over 4. The 4x squared minus 8 to the third becomes u to the third. And then the 8x dx is a du. A little bit of algebra here. I move the 4 out front. 2 over 4 will give me a 1/2. I'm going to distribute the u to the third, giving me u to the fourth plus 8u to the third du. When we evaluate the antiderivative, we get an antiderivative in terms of u. And then finally, we want to replace this to be in terms of x. So I'm going to distribute my 1/2 through here. That'll give me 1 over 10 times 4x squared minus 8 in parentheses to the 5th power plus the 1/2 and the 2 are going to cancel. So we're just left with 4x squared minus 8 to the 4th power plus c. There's our final answer for example 3. And we'll finish with this example. Here we have an internal function in the denominator. So let u be x cubed plus 8. Then du is 3x squared dx. And if I look at my numerator function, I only need a 3x squared out of that 9x to the 5th. That is going to leave me in excess of 3x to the third. 3 times 3 is 9. X squared times x to the third is x to the 5th. This is needed for my du, and this is my extra. I'm going to move the constant out in front. So we have 3 times the antiderivative. I need to solve for x cubed from my u substitution. So x cubed is equal to u minus 8. The denominator is the square root of u, and then the 3x squared and the dx give me a du. When we divide u by u to the 1/2, that gives us u to the 1/2. So we will rewrite the integral again. And when we divide 8 by u to the 1/2 power, it gives me minus 8u to the negative 1/2. Now we can apply the power rule. U to the half, add 1 to the exponent is 3 halves. This gives me 2/3 u to the 3 halves. U to the negative half, add 1 is u to the positive 1/2. When you divide by positive 1/2, you're multiplying by 2. So this is minus 16 u to the 1/2 plus c. When we distribute here, the 3 in the numerator cancels with the 3 in the denominator. So we're going to be left with 2u to the 3 halves. Let's bring this up here. When we multiply 3 with the 16, we get negative 48. And then we have our plus c. Finally, let's return u to its x variable form. So 2 times x cubed plus 8 to the 3 halves power minus 48 times x cubed plus 8 to the 1/2 power plus c.